So I'm going to be talking about fluctuation theorems and irreversible processes in statistical thermodynamics. The goal will be showing that there is an alternative method for deriving equations of state via processes that do not come even close to thermodynamic reversibility. And the entire talk is going to be devoted to unpack this, and we will make use of a fluctuation theorem that has been already mentioned here by Eugene and David, called Jasinski's equality, which states that the expectation value of the exponentiated work time beta, the inverse temperature, equals the exponential of the free energy difference between two states, the initial and final state of the process in which work is done or extracted, which is of course equivalent to the second expression there. And the relevance of this is both theoretical and practical. I think it sheds light on the relationship between fluctuations and irreversibility at different scales, as well as on the relationship between equilibrium and non-equilibrium thermodynamics. And moreover, it provides further resources for the application of thermal concepts to regimes where systems are constituted by a small number of degrees of freedom, such that they may be governed by fluctuations, and where thermodynamically reversible processes are more and more difficult to approach. I'm going to be explaining these things. I'm going to focus today in particular in the second point, and if we have time, I'm going to say some things about the first one, but the main point is going to be the second one. In general, in thermodynamics, the states are described by a few parameters, which we call the functions of state. And the functions of state are in general well-defined only in equilibrium. As it has been as it's pointed out in textbooks, but in the philosophical literature, David has been very explicit about it. The predictive power of thermal physics relies on the equations of state, which provide functional dependencies among the state functions, enabling those predictions. And in both phenomenological and statistical thermodynamics, the equations of state are defined and derived by considerations of equalities between the functions of state. The question then is in which circumstances those equalities hold, and the standard answer is that the equalities hold for the special case of quasi-equilibrium and reversibility. So connecting with the aim of the talk, we'll show that there is an alternative method for deriving the equations of state via processes that do not even come close to quasi-equilibrium or thermodynamic reversibility. So first, a warning. What's a thermodynamically reversible process? Well, it's one in which after the process is completed, the original state can be recovered without having to spend a net positive amount of energy, such that we say that these processes do not dissipate. Of course, we know that these processes do not exist in nature nor in the laboratories, because they are conceived as limits over sets of irreversible processes where the thermal imbalances vanish, go to zero. And also we don't need these processes to exist. All that is needed is that there is nothing in the physics that prevents to get arbitrarily close to reversibility. And so every time that I say reversible process, for the purpose of this talk, I'm going to mean processes that come arbitrarily close to being reversible, but that do not need to achieve exact reversibility. And this goes in a different line from what Wayne has explored, which is the modifications needed for thermodynamics to literally do not appeal to reversibility at all. So the plan is the following. I'm going to remind you the role of reversibility in phenomenological and statistical thermodynamics. Then I'm gonna introduce and discuss in detail Jasinski's equality, and I'm gonna show how we can use it to derive equations of state from far from equilibrium processes. And if time allows, because I'm gonna try to not speed up, we are gonna discuss how these bridges micro and macro irreversibility. So as I said, the state of a system is individuated by the functions of state. An example, for example, for an ideal gas is the internal energy, the pressure, the volume, the entropy, and the free energy. And the functions of state bear dependencies between them. How do we obtain those dependencies? Well, we know that one way to do it is by learning the entropy of a system as a function of the internal energy plus other variables. In the case of an ideal gas, which is the simpler, we have the entropy as a function of the volume, the internal energy, and the number of an Avogadro's number. Then from this, we can derive the dependence of the energy on Avogadro's number, the heat capacity at constant volume, and the temperature. And we can derive, of course, the ideal gas law. But this pushes the question back in some sense, because how do we derive and compute and define entropy for different substances in general? We won't assume that God comes here and tells us the entropy for different systems. So in phenomenological thermodynamics, we have that the first plus the second law entail the existence of a function S, which is uniquely defined up to an additive constant for processes that can be connected reversibly. So in a cycle, for example, the entropy of the heat exchanged reversibly, or the integral over the heats exchanged reversibly at some temperature, is equal to 0. And we know that only if the integral is taken over a reversible process, S depends on the initial and final states of the process and nothing else, such that we can consider it a state function. Of course, we don't have to run full cycles. We can just have two arbitrary states, and we will have entropy. We can define the entropy of a system as the entropy of the initial state, which can be chosen arbitrarily because everything that matters is the entropy differences, plus the heat exchanged over a reversible process with a heat bath at some temperature. So the integral here is taken again over a reversible process in which heats are exchanged at some temperatures, again reversibly. If the process cannot be connected reversibly, there is, as Wayne has shown, a family of functions satisfying a strict inequality, such that we only get bounds. Similarly, and this is a quantity that's going to be important because we saw that Jasinski appears in Jasinski's equality. We can define the free energy at some temperature given some external parameters, and this free energy, which equals the internal energy minus the temperature times the entropy, is also bears a relationship with the work done or extracted from a system. Of course, every time that I say work done or extracted, we know that work is not a state function. There is nothing like the work content of a system. It's energy exchanged in terms of work, which means that energy exchanges associated to changes or variations in the external parameters, like lambda here. We know that there is this inequality, which I call the Helmholtz inequality, because associates the Helmholtz free energy to work. And we know that the equality there holds only in the case of reversible processes. In statistical thermodynamics, we know that the state of a system is represented by a point in the phase space. The phase space is equipped with a Liouville measure. And the statistical thermodynamical analog of a thermodynamic state is given by a probability distribution over the phase space and a family of Hamiltonians, which are parameterized by lambda. Again, lambda are the external constraints, which can be understood as generalized forces. And we associate the work with the energy exchanges due to the manipulation of the external parameters. In statistical thermodynamics, we are concerned, one of the concerns or one of the quantities we're interested in are the expectation values of quantities, such as, for example, the internal energy of the system. And I said that, so the thermodynamic state, the statistical thermodynamic state is given by a probability distribution and Hamiltonian. We will focus here on a specific distribution, which is the canonical distribution, which is given by the so-called Maxwell-Boltzmann factor and the partition function, which is usually presented as a normalization constant, but we will see that it's very important because it bears dependencies. It depends on beta, on the inverse temperature, and on the external parameters. So to connect with phenomenological or historical thermodynamics, we can define an entropy function if we have. Now we replace though the expectation, heat exchanges by the expectation value of heat exchanges at some temperature, and we have similar conditions, analog conditions, as in phenomenological thermodynamics. We can define a state function, which is going to be given by S G. We will see why. I mean, you know why. Which is going to be defined only over reversible process, connecting a pair of states. And it can be shown that as Gibbs did, then Tolman for the quantum case, and Owen and Myrvold in modern, Owen, Maroney, and Wayne in the modern version, can be shown that if there is a reversible process connecting the pair of states, then this SG, this SG function is takes the form of the Gibbs entropy. For any other pair of states that cannot be connected reversibly, this will just give, you will have a family of functions satisfying this is a typo, should be a strict inequality because the process cannot be connected reversibly. So if the process cannot be connected reversibly, everything that you will get is a strict inequality bounds on the, you will get a family of functions that will be bounded by the heat exchange, the expectation value of the heat exchange. So sorry for the typo there. So the second law implies the existence of a function S with the following properties. S is defined as the ratio between two states. S is uniquely defined and computable if there are in the limit, if there is in the limit a reversible process connecting two states. And only in these circumstances, we can, the entropy S, be it thermodynamic entropy or Gibbsian entropy, can be used as a state function, and from which equations of state can be derived. A third property, which I'm not going to delve into now, is that S is defined in relation to a set of external parameters for which a reversible process is available. Someone will say, okay, but wait a minute. statistical thermodynamics gives you more resources for deriving equations of state and for defining entropy. I mentioned the partition function, right? The partition function, which is usually just presented as a normalization constant, can be used as my favorite textbook in thermodynamics says, Blundell and Blundell, very picturesquely.
Yeah.
Yes. Here.
No, in the orange box.
Up here.
Yeah.
Yes. Yeah, sorry.
It's invisible.
Yeah.
It's there.
Yeah. So the partition function depends on the temperature, yes, and the Hamiltonian. And we know that if we have the partition function of a system, and which implies knowing how it depends on temperature, yeah, the beta, and the Hamiltonian, and through the Hamiltonian on the external parameters, we can derive everything from it, right? We can derive the expectation value of the energy, we can derive the Gibbs entropy, we can derive, importantly, the free energy. But the question then is how we can know or learn the partition function for a complex system. If you are not a Laplacian demon, good luck computing from first principles either the partition function or the Hamiltonian for any non-ideal system. Which the point being that we still need, for all practical purposes, these processes that come arbitrarily close to being reversible. If we want, for example, to have a uniquely defined entropy of a system, and we want to use it to derive equations of states. I mentioned it for the case of phenomenological thermodynamics already, the free energy. This is the analog, the statistical thermodynamical analog, the free energy for a given temperature, given some external parameters, will be defined as a relationship between the reverse temperature and the logarithm of the partition function, such that we can have the free energy difference between two states is given by the difference in the logarithm of the final state and the initial state. And we can get an analog of Helmholtz inequality with expectation values instead of the work. So the expectation value of work. So we have that the expectation value of the work done on a system will be greater than or equal to the free energy difference between two states. And we know, of course, that an equality is way more informative than inequality. If I tell you that you need at least 500 euros to go to a conference, so you want to go to a conference and you don't know how much the fees are, you don't know if you can afford it, and I tell you, oh, they are at least 500 euros, maybe that's not that informative for you. You cannot make an informed decision about whether you can go or not, but if I tell you they are exactly 500 euros, then you can take, for example, a very informed decision. Just the point being that an inequality is way less informative. You cannot use it to get precise values. Notice that there is, in phenomenological thermodynamics, a necessary condition for reversibility is that the processes take place arbitrarily close to equilibrium, as I mentioned at the beginning. But when there are fluctuations, one needs to consider expectation values, and a condition is that the expectation values have to be distributions of the probability distributions have to be tightly focused on the expectation values. So, for example, if reversibility is the condition in which after the completion of a process, you can return it to the initial state without having to spend a net positive amount of energy, then you need the distributions over the work to be picked on the expectation value. And of course, the smaller the system is, the more it will fluctuate. such that if you want, over the process, sometimes you are going to exchange work, with the bath, with the environment, and this work is going to be maybe way above the average. Sometimes it's going to be way below the average. But what is important is that the distribution, all these work exchanges add to 0. And for this, you need to consider lots and lots and lots of work exchanges, such that by the weak law of large numbers, the distribution approaches the expectation value. So if the smaller the systems are, the fewer degrees of freedom they have, the more difficult it gets to have this slightly peaked, to have this distribution peaked on the expectation value. You need to wait longer and longer times. But there is an alternative. So fluctuation theorems are a family of results that provide equalities between the probability distributions of thermal quantities. And the interesting feature is that these equalities hold independently of whether the process is reversible or not, whether the process takes place close to equilibrium or not. We will use, as I said, the Jasinski's equality, which says that instead of focusing on the relationship between the free energy and the expectation value of work over a process, we will take the expectation value of the exponentials, the expectation value of the exponentiated work and the exponentiated free energy. How does this work? Well, consider a system coupled to a heat bath at constant temperature. What the Jasinski equality tells you is that if we measure the work exchanged by the system over a set of processes, we can compute the free energy difference between the two equilibrium states at the same temperature. And here is a recipe for doing it. So consider a heat bath and a system initially uncorrelated, and then you let them exchange energy until they get to equilibrium. And assume that during the equilibration process, the external parameters of the system are held constant at some value. So imagine a reservoir and a gas in a box. Imagine that you push, the box has a piston, you push the piston up to like 1/4 of the total volume, such that the gas has like 1/4 of the total volume available. Holding that fixed, you couple it to the reservoir, and you let it equilibrate, having the piston fixed. This will enable us to represent the state of the system by a canonical distribution for the initial Hamiltonian and the value of the external parameter and the external temperature. This Hamiltonian will have, this canonical distribution will have associated with a partition function. Here, there is the method. So this is the lambda 0, the external parameter will be pushed to have 1/4 of the total volume available. And we define a protocol in which we are going to pull the piston from 1/4 of the total volume to half of the total volume. And this protocol will take place. We don't assume that this protocol or this process is reversible. So we are going to again pull the piston from 1/4 of the volume to half of the volume. Half of the volume will be our lambda 1. And this pulling the piston, carrying out this protocol will induce a state transition. Notice that the initial state is canonical, but we don't assume that the final state is canonical. We have a final Hamiltonian and a final distribution, which does not have to be canonical. We thermalize the system, and after we thermalize, before we carry out the protocol, we decouple it from the heat bath. Why? because this will enable us to individuate the energy exchange over the process to the work. Will enable us, here there is like a summary of what we have been saying. This will enable us to identify the difference between the initial and final Hamiltonians with the work done over the process. And because the Jasinski's equality is about the expectation values, we will repeat this process several times. Every time we will thermalize the system with the same initial, with the same reservoir at the same temperature, and with the parameter, the initial parameter of the Hamiltonian fixed at the same value, that is 1/4 of the total volume. And we will carry out the protocol several times. Because we thermalize the system every time, we can assume that work is going to be independently and identically distributed. And at this point, of course, we could estimate the expectation value of the work. Every time that we carry out the protocol, we measure the work, and we could take the expectation value by averaging over the works done over all these trials, and this would lead us to the standard notion of free energy, right? The expectation value of the work will have to be greater than or equal to the free energy difference between the initial and final states. But what we want, what Jasinski tells us, is that we want the expectation value of the exponentiated work times the inverse temperature. And for this, we will measure the work, and then every time we will compute the exponential of this quantity, and then we are going to average over those quantities. And by the weak law of large numbers, the more trials we perform, the average will get closer and closer with the expectation value, and we can make it as close to the expectation value as we want by performing more and more and more measurements of work. What can we do with this now? Well, it's what Jasinski tells us is that we can have the work. From the work, we can identify with the difference in the Hamiltonian of the initial and final distribution, and then we just do the canonical. We apply the canonical recipe, right? With the canonical recipe, we plug in the canonical distribution, we unpack it, we assume that the Hamiltonian, the system evolves unitarily or by Hamiltonian evolution, which is method preserving. This enables us to rearrange these guys here. And we get that from the expectation value of the exponentiated work equals the ratio between the partition function associated to the initial and final states. We previously defined the free energy in terms of the partition function, and the free energy difference as the ratio of two partition functions, and hence we get Jasinski's equality. Comments. Of course, as I mentioned already, we have made no assumption about the nature of the process. We have carried out a protocol in which we have thermalized the initial state, and we get a state that is not thermal. I'm going to comment on this too. On a final state that is not necessarily thermal, or a final distribution that is not necessarily canonical for the final Hamiltonian and the temperature of the system. And all we have done is carrying out lots of processes, and we have measured work. And I have cheated a little bit because what are these two sets? They are not really the partition function. They are numbers. They are the values of the canonical states associated to the initial and final Hamiltonians. But we have learned only what's the value of the partition function for the final state, for the final canonical state associated to the final Hamiltonian. but nothing else. So we cannot technically use these sets because these are just values, they are not the functions. We cannot use them yet to derive equations of state because we don't have the dependency of the partition function on the parameters or the temperatures. And we have not assumed that the final state is canonical. Actually, it may not be because probably will not be because every time we carry out the protocol, the work will fluctuate. Everything that we have got are the values of the partition function for the finals, for the state that is canonical for the final Hamiltonian. And we know that for every Hamiltonian and every positive temperature, there is a distribution that is canonical. And this distribution that is canonical, and this set here is the partition function for the of the canonical distribution associated to the final Hamiltonian and the temperature of the heat bath. So as I mentioned, we still don't have the partition function. We just have values of the partition function for the initial and final state. For this, we need to compute the partition function, how it changes when we change the parameters first, and then how it changes when we change the temperature. For this, for the case of the parameters first, we will carry out m set of processes, lots of processes, each time starting from the same initial state, the gas with the piston pushed to 1/4 of the total volume, because everything that matters are difference between the free energy of two states. We will take the free energy of the initial state as a reference state, and we will carry out sets of processes. So we already carried out one in which we pull the piston from 1/4 of the total volume to half of the volume. Now we will do it for half of the volume, then for 3/4 of the total volume, and then for the total of the total volume. We are going to pull out the piston completely, and we are going to measure the work every time starting from the same initial state in these different sets. So we are going to have one set in which one full set in which we're going to do lots of measurements of the work, in which we start from the same initial state and we go to the same final state, half of the volume, say. Then we are going to do another set of process in which we are going to measure the work. We are going to compute the exponentiated of this quantity. We are going to do the expectation value, and we are going to compute the free energy difference and the partition function for that final state. And that we are going to do lots and lots and lots of this. And from this, we will get the dependence of the partition function on the external parameters. And this, everything that allows us to do is get information about the equations of state at the same temperature. We have not considered varying the temperature because we don't have the dependence of the partition function on different temperatures yet. So this is still restrictive. We cannot use it to derive equations of state. But we know that there is a relationship between the expectation value of the energy of the system and the partial derivative of the logarithm of the partition function with respect to the temperature, and we can exploit this to get dependency of the partition function on different temperatures. So we will, for each of these sets of processes, for each of and for each partition function that we get associated to these sets, now we are going to vary the temperature slowly. No, not slowly. Sorry. We are going to change the temperature, and we are going to measure the temperature for smaller differences. But we won't assume at all, again, that the temperature the exchange of energy leading to a difference in temperature is reversible or anything like that. Everything that we need is two different temperatures for the system and the systems are associated to different partition functions at different temperatures. So if we do lots of experiments with small temperature difference between them, and we measure the internal energy, we compute the expectation value, and then we do numerical integrations, then we can estimate the dependence of the partition function now on of the dependence of the partition function on the temperature. And with this, we can use what Blondel and Brundle picturesquely call the sausage machine. We can introduce the partition function, and we can compute the entropy, for example, without invoking any reversible process. So what's the relationship between the Jasinski's equality and the second law of phenomenological or historical thermodynamics? How we recover it? Well, we know that from the Jensen's equality, inequality entails that for any convex function and random of a random variable, the expectation value of the quantity will be greater than or equal than the function of the expectation value, for which the Jasinski's equality entails that we recover the Helmholtz inequality. This means that the Jasinski's equality weighs heavily on likely fluctuations. Applying the Jensen inequality smooths them out, and we recover the fact that those fluctuations become exponentially unlikely in the regimes in which the systems are composed of a very large number of degrees of freedom. This is something that I learned recently from discussions with Wayne. Although I don't know if he will agree with this in particular. Now, if we consider two more quantities, the variance of a random variable and what I will call, although I don't think it's the right name, the spread of the probability distribution of convex functions, and we apply it to the Jasinski's equality, then we get that the difference in the expectation value of the work minus the free energy difference is associated to this spread in the work distribution. And if we compare this with the standard definition of irreversibility, or the work dissipated, which is the difference between the expectation value and the free energy difference between two states, such that, and we know that for every that this quantity here, which is the sometimes associated to the irreversible, called the irreversible entropy production, is greater than 0 for any irreversible process, and gets arbitrarily close to 0 as the process gets close to reversibility, to being reversible. We can see that this quantity, the spread in the probability distribution of work, is a measure of dissipation and then an ends of irreversibility. And I think that this provides insights that are closely related to what has been called the fluctuation dissipation theorems in another context about the source of irreversibility. Here we have that for every process in which the spread of the probability distribution is not tightly focused, we will have an inequality here, and we will recover the Helmholtz equality, the special case in which equality holds in the Helmholtz inequality, only in the case in which the fluctuation of work can be neglected, which means that we recover in some sense macroscopic reversibility and the ability to approach it arbitrarily close, and the assumption that we can approach it arbitrarily close in phenomenological and historical thermodynamics in terms of the possibility at the macro scale of neglecting fluctuations. So in some sense, reversibility corresponds to the limit in which the dissipation vanishes or goes to zero, which for processes coupled to a single bath at constant temperature occur when the distribution of work is tightly peaked on the expectation value, becoming thus a dispersion-free quantity. So in these circumstances, reversibility is associated to dispersion-free, to work being a dispersion-free quantity. Reversibility then is associated to the lack of fluctuations, and this explains why in phenomenological thermodynamics it is safe to assume that every pair of states at the same temperature can be connected reversibly. In the cases in which the temperature of the system changes, the spread of the spread will not be on the work. The spread associated to irreversibility will not be on the work distribution of work, but on the distribution of energy. So to conclude, the derivation of equations of state requires reversible processes, which get more difficult to perform as we apply thermodynamics to new regimes where fluctuations cannot be neglected. And because fluctuation cannot be neglected, and because we need the probability distributions to be tightly focused on the expectation value, we need to wait long times for the processes we need to carry out the processes very slowly and wait long times in order to be able to compute these reversible processes. By long times, I mean long times, of course, in relation to the equilibration scale. And here there is an alternative method, which requires a large amount of measurements to be carried out. However, it does not rely on fine-grained powers of manipulations needed to perform this, to approach reversibility at the microscale. And we have obtained this approach by a different kind of limit. Still, reversibility is associated to a limit, but it's a different one, while in phenomenological thermodynamics, it is the limit in which the thermal imbalances approach to zero, in which we get arbitrarily close to reversibility. Here, we have, in statistical thermodynamics, this happens in which the limit in which the processes take place arbitrarily slow in relation to the equilibrium time scale. And by Jarzynski's method, we have that reversibility can also be approached in the limit in which the far from equilibrium processes are very large. I had this bonus for the roundtable relating the Boltzmann versus Gibbs, but I'm going to skip it because we already discussed it yesterday. I'm just going to say that if there is something like a Boltzmannian approach that considers that probabilities do not have to play any role at all in in thermodynamics or statistical mechanics or in statistical thermodynamics, if you think that probabilities should not play any role in thermodynamics, then these kind of results, as David pointed out yesterday, will not be available and we cannot make sense of them. And with this, I conclude. Thank you.
We have time for questions and discussions, starting with David.
Okay, great. Thank you. So I have a technical thing about the Jarzynski equality, which perhaps I'll come back to this time, but let me ask something more conceptual about what you take to be happening here. So here's my concern. I'm not quite sure I know what's being meant here by the idea that deriving the equations of state requires quasi-equilibrium processes. I mean, here's the thought. So we're in a statistical mechanics regime here. Now, the thermodynamic entropy in normal phenomenological thermodynamics is supposed to be non-decreasing under any adiabatic process, not just slow ones. I mean, it's the reversible limit, it's constant. But you know, if I take my cylinder of gas and shake it hard, for instance, that counts as a far from equilibrium process that moves me away. Now, in a statistical mechanical underpinning of equilibrium thermodynamics, I can just posit the Gibbs entropy. It's a perfectly well-defined function of the distribution. I can prove trivially that it's constant under Hamiltonian flow, and I can observe that its value for given conserved quantities and parameters is always less than or equal to the Gibbs entropy evaluated for the canonical distribution for those same values of the parameters. So I can derive the fact that under any transformation, I can carry out fast or slow adiabatically. S is non-decreasing and increasing unless the process is asymptotically slow. And that gives me the fact that entropy is that the equilibrium entropy is non-decreasing, and the equilibrium entropy just by elementary calculation is beta E plus log Z, and I can derive the equation of state from all of that. So, you know, without prejudice to the fact that the Jasinski equality teaches quite a lot of interesting things about what the nature of the difference between the fast and slow processes are. I agree with all of that completely, and that's really interesting. I'm not really seeing what this is contributing to getting out the equations of state. It just seems to be getting us out an already known relation between the entropy and the partition function.
Yeah, thank you. That's a very good point. So, please correct me. I'm happy to think about it more. What I will say is that in order to compute the entropy, right? As you said, you need to know the partition function, right, of the system. The question that how I want to answer you is, how do we get that partition function for a state how can we compute the partition function for a system that is, for example, the example that Jasinski uses to show his equality is like a rubber band, right? That you stretch it. How will you compute the Hamiltonian and the and the partition function for that system?
So, I mean, Jasinski doesn't change the definition.
From first principles.
Yeah,
right?
It's e to the minus beta h integrated over the phase space. I mean, that might be a difficult calculation. It might be a difficult bit of microphysics to determine h. It might be a difficult piece of computation to find a tractable approximation to the integral.
Right.
But that's none of the Jasinski equality doesn't change that.
Right. Okay. The Jasinski's equality, I would say, changes the possibility, so enables you to be able to approximate that quantity better, to compute the partition function, not deriving it from first principles, but if you compute the work, if you carry out a set of processes on this rubber band, you will be able to get the specific value.
Do you mean compute, or do you mean empirically measure?
Measuring and computing, right? I mean, no. If you can measure it, if you have the value, you can measure.
Okay, and that's a good point, but it's a very different observation. That's not. I mean, that's not a theoretical physics thing. That's a cool piece of experimental technology made available to us by the fluctuation theorems.
Yeah. Okay. I should emphasize that it's purely practical, or experimental result.
Yeah, I mean, distinguish the two. I've got no problem with practical results, experimental or theoretical.
Yeah, but
this isn't a technology to help you compute it. If you want to calculate the work thing, you're going to need the partition function. It's only if you're in the lab and you want to run it lots of times.
Right. Okay. Yes, I see. Yeah. Okay. Thank you. I should be way more clear about that. Yeah. Thank you.
I just want to make a clarification point. I mean, David's absolutely right. Like if I know the Hamiltonian, right, and I have the ability that I can write down the partition function, and given unlimited powers of computation, I could compute the equation of state. But as Pascal said, briefly, I think you should emphasize this more. For lots and lots of systems, we don't do that calculation, right? But we can measure entropy differences. And typically how we measure entropy differences is by slow processes, measuring heat changes. And I think what you want to say is, hey, here's another way to measure free energy differences. Yeah, that's 80%. I just want to say something about something that David said. So take the example of free expansion of a. So you're talking about non-decrease, take an example of free expansion of a gas. Let it expand. Okay, fine grain Gibbs entropy is non-decreasing, right? And in fact, if this is isolated system, the difference is 0. Does that correspond to the I'm sorry, does that correspond to the difference in thermodynamic entropy? Given ordinary classes of manipulation, no, it doesn't. This has higher entropy, right? And what we ordinarily do is imagine a reversible process connecting them. Can you compute the difference between thermodynamic entropy? If you imagine some restricted class of manipulations where you can't have anything, even you've got two states that aren't connected by anything even close to a reversible process, there'll be a family of functions that have that non-decreasing property won't be uniquely defined. And if you want a uniquely defined entropy difference, you have to be considering a situation in which there's you can get as close as you want to reversibility.
Hi, thanks for a very nice talk. So, I think I'm still maybe I just kind of lost it along the way. But so what was the claim with regard to reversible processes and what you were saying about your result? So I think it was in your summary slide, like just before this one, I think. So I think you were making some claim about deriving these relations without reversibility or something like this. Or could you restate that so I kind of understand that?
Measuring, yes. So you mean the main claim?
Yeah.
So that we can estimate or measure the partition function without requiring reversible or processes that come arbitrarily close to being reversible.
Okay. Through something like a Jarzynski equality type experiment is
right.
Is that
because
okay?
So what we needed is that we need an equality to hold, and this Jarzynski gives you the means in which an equality will hold for processes that are not arbitrarily close to equilibrium, for processes that are actually arbitrarily far away from equilibrium. It doesn't matter how the process takes place, and the equality will hold anyway. And we can use that equality to estimate or measure the entropy difference and then derive everything we want about the system.
Okay. Maybe I'll just make a small remark. So I think the kind of line of your your kind of line of research is quite parallel to like the one that me and my supervisor are working on. But of course, for our side, we are really trying to, I think the spirit of it is to really kind of dwindle down these fluctuation theorems to some kind of core derivation, right? And what we do on our side is to really invoke these statistical rules like Bayesian reasoning to explain these things. And one thing that he does, my supervisor's paper at least, he argues that you can actually understand these fluctuation relations as just normalizations of the reverse process. So just now you had the piston thing where you kind of push it forward, you push it back. Yeah, so he basically tries to prove that it's essentially just making sure your reverse process is normalized. And you get like these Jarzynski situations. Then after that, we followed it up in another paper. I can kind of send these to you later. I'm kind of curious whether you have engaged with like Crookes kind of Markovian approach to this, like not the Evans-Searles type derivation, whereby there are these trajectory bundles and everything, but rather with these Markovian things. I think it will be interesting if you can do something similar with that approach. Of course, that's for Crookes. Then Crookes, you get Jarzynski, but you did this kind of directly to Jarzynski instead. Yeah. So yeah, just remarks.
Yeah, no, I have not looked at that, but I should. Please, let's talk later.
Yeah, for sure. Yeah.
Thank you.
Hi, thanks Pascal for the nice talk. Yes, I wanted to elaborate on these points about the fluctuation theorems by analyzing forward and backward processes, because an assumption that I find suspicious in the way that you're looking at it is that you assume initial thermal equilibrium and then you let the system kind of evolve. But it's not clear to me what is happening with the evolution protocol lambda that you have. But because it seems like you then disconnect your system from your thermal environment and then you let your protocol act. And this sounds kind of weird. Both processes should happen simultaneously, like the interaction between the system and its environment and the driving that you're doing on it. And I think that looking at the fluctuation theorems from the perspective of forward and backward processes, it enables you to compare the probabilities of going backwards and forward. And then the way in which to interpret the fluctuation theorems there, at least the way I do it, is you get to the conclusion that one direction is exponentially more likely than the other. So this gives you like a count of how many processes that you repeat many times it gives you the proportion of processes that may violate the macroscopic second law of thermodynamics, but on average, the second law of thermodynamics falls. So when you look at these kind of approaches to derive fluctuation theorems, you can realize that there are two basic assumptions, and this is that your initial state has to be thermal, as you assumed. And the other assumption that you need is micro-reversibility. Basically detail balance, but micro-reversibility in the sense of the Hamiltonian equation. So if you're in classical systems, you can do this by looking at how the phase space point of your system evolves when you take the reverse sequence of the time protocol that you're applying on your system. And if you're looking in quantum systems, you can do this with the unitary evolution, and you have another quantum micro-reversibility principle that enables you to derive the fluctuation theorems with these two assumptions. But in that case, then I think that the question that you're asking about reversibility or irreversibility makes much more sense. So yeah, I don't know whether you have any comment.
Yeah, thank you. I see your point about the probability distributions of forward and backward processes. That's like other way of deriving it, right? Mm-hmm. Like using explicitly Crookes theorem, or as a consequence of Crookes fluctuation theorem. Here I just there are different ways of getting to the Jarzynski equality. Here, indeed, you are completely right that I assume that you thermalize the initial state and then you decouple it. That's not necessary, but it just facilitates the distinction between heat and work. So just to be able to measure work easily, I decouple it from the system before carrying out the protocol. So sorry, from the reservoir or from the environment, such that I can get the work by the difference in the Hamiltonian between the initial and final states. That's the whole purpose of it.
Yes.
But of course, you can do it with the system evolving coupled to the heat path too, and then you have, you can do that too.
Yes, and there is something else that is quite nice, that I find quite nice, but I think that is something that it's worth of more precise philosophical interpretation, because in theoretical physics we are not so worried about some of the assumptions that you are worried about, and is that in any entropy producing process that you may describe by means of a probability distribution function, you can derive very general fluctuation theorems by just looking at the quotients between producing certain amount of entropy and producing the negative amount of entropy starting from the final state. And this is a very general statement about probability distributions of entropy generating processes that I think is worth looking at.
Thank you. Thanks.
Yes. Well, thank you. I'm not a bit talking a little bit fast for me to completely understand what you are saying. And but as a introduction, when to say that when you talk about reversible processes, you're talking about a topic that is historically a quagmire of confusions. There's an enormously large variation of meanings that different authors attribute to the term reversible process. Now, I'm aware that you started out with a definition of what you mean by so I'm not saying that you contribute to the confusion, quite the contrary. But when you come to your conclusions, as far as I understand, you say there's an alternative method to measure the partition function if you have no access to reversible process. And so you say you obtain this by taking a third kind of limit, which in the case of phenomenological thermodynamics refers to a limit in which thermal imbalances approach to zero. And in the case of statistical thermodynamics, a limit in which the processes take place very slow.
Yeah, I should be more careful with the second one, especially.
If you look at what say John Norton understands by a reversible process, it is a
okay, thank you. Yeah. If you look at what John Norton means by a reversible process, it is a limit. It's not a process. It's a limit of processes, each of which is irreversible, but in which the thermal imbalances approach zero. So on John Norton's terms, your proposal makes use of what he calls reversible processes. If you consider the limit in which the processes take place very slow in relation to equilibrium timescales, then I'm thinking of Planck in his lectures on thermodynamics, and slightly later Cacateodori, 1906. Planck talks about processes which he calls taking place infinitely slow. And a little later in his book, he defines them to be reversible, or more precisely in the German edition, he says umkehrbar, to be distinguished from a later notion of processes which are reversible. Unfortunately, in the English translation of his work, those distinctions have become washed out because both terms are translated as reversible. Carathéodory takes a similar, mathematically more sophisticated approach as Planck, and he uses a different word, quasi-static, to describe that limit sequence of processes. But the idea is the same. They have to take place very, very slowly. So, and once again, what Carathéodory calls quasi-static is in a large tradition of the thermodynamical literature, usually called reversible. So, what you're proposing might be new under your definition of reversible processes. But it might coincide with what other authors have called reversible processes. And the worry can arise, like those authors might look at your work and say, hey, that's just what we've been saying. You need reversible processes. And you, in their opinion, you won't have gotten away from the requirement that you need access to reversible processes. So I'm just worried about the background confusion in the literature on what reversible processes mean, in order to understand what your conclusion brings to the table as a new result.
Thank you. That's a very good point. So yes, I completely agree that there is lots of confusion about the relationship. About what reversible processes are, and about the relationship between reversible processes and quasi-static processes. What I would so help me understanding this. Even in Norton approach, for example, right? It's sets of processes that are irreversible, but that get arbitrarily close to being reversible, no? Or all those processes, the set of processes can be arbitrarily far away from equilibrium. Can they? They have to be.
That's in Norton's approach not very clear to me, because he uses this term thermal imbalances, or at least the word imbalances. And I'm not quite sure how he defines that. So there are, and also what it means to have those imbalances approach zero.
Right.
And I'm also not quite sure what it means to be far from equilibrium. So Carathéodory is slightly more explicit about it. It's, you could take a limit in the examples you've used, where you just pushed out the piston, and you can take a limit in which you go from an initial position of the piston to a final position of the piston. You could take a limit in which the increment in the volume of the system becomes smaller, and take more and more steps, and take a limit by taking the increases smaller and the number of steps larger, to approximate a reversible process. Well, that doesn't succeed, because in each step there's an entropy increase, and in the limits the entropy increase is still there. So the limit is not a reversible process. In Carathéodory's consideration, it's clear that that is not a quasi-static process. But in John Norton's approach, I wouldn't know. Because the imbalances are small. Is a large fluctuation of equilibrium if I just increase the volume suddenly by a small amount? Well, it's large enough to matter in the end result. But in order to say whether the difference from equilibrium is large or small, you need some kind of metric or topology to judge that. And since deviations from equilibrium can come in infinite many ways, it's not completely evident how you can do that. What is far from equilibrium, what is close to equilibrium? And can you compare all non-equilibrium situations by one single distance from equilibrium? I guess I went off on a tangent here, but
no, but it's very good for me to have. I will think about that definitely. I definitely have to be more precise about that.
Yeah, I mean, I think I'm going to be talking about this in my I just made reference to my talk. For those of you who haven't heard, unfortunately, Giovanni Valente is ill and won't be able to give his talk this afternoon, and I'm going to substitute it for. I'm going to do the after lunch talk. So what you're saying, Jos, I mean, I'm going to say a bit about this in my talk, but this is how I think I think it. So suppose we have some process that goes from some state to A to B. And we can ask, is there another process that takes you back to from B to A in such a way that that's what's that? Nearly invisible. So if I go to A to B, is there a way to go back from B to A in such a way that the integral of dq over t over the whole process is 0? And if so, then we'd say the process that went from A to B is reversible. And how close we can get to 0 on that is a measure of how irreversible the process is. Yeah. Right.
That state phase. That state space consists purely of equilibrium states.
True. But if we go to the statistical mechanical context, right, so early on, Pascal said, look, we're going to take the statistical mechanical analog of a thermodynamic state is going to consist of a probability distribution over state space plus Hamiltonian. And so that gives us a, if that's our statistical mechanical state space, then we've got things that don't correspond to that.
That doesn't matter. I mean, you can reconstruct the thermodynamical state space or the points in those state space as representing probability distributions on a statistical mechanical phase space. But if all those probability distributions belong to a family of canonical or at least equilibrium distributions, then there are still representations of equilibrium.
Right, exactly. Then that, so yeah, so that's exactly right, which is why it's very important that he's considering a wider class of probability distributions. At a certain point, you had a slide.
But if,
At a certain point, you had a slide where you said you're assuming that the initial distribution is canonical. You're not assuming that the final distribution is canonical.
right, but then that final distribution is not represented by a point. In your
Exactly. Yeah, that's the point. Yeah.
diagram. So this diagram would be misleading.
Okay, this diagram was what was 2 points in that wider state space in the space of probability distributions on phase space.
Ah,
I think you might be using a version of Jasin, or proving a version of Jasinski's equality that's a little narrower than you need for your purposes. So if I understood the setup correctly, your version says, start my system initially in equilibrium with a large heat bath. Yeah, you want to go back. Yeah, so I think, go to the next slide. No, sorry. Let me just explain and you can find the slide subsequent to that. As I recall, the way you set this up is I start the system and the heat bath initially uncorrelated. I allow them to reach equilibrium. I then disconnect them and evolve the system adiabatically. Yeah, this is the decoupling. So you don't need the decoupling to derive the Jasinski equality. And you'd better not have it for your purposes.
Okay.
Because if you do have it, then the asymptotic limit you get when you vary the parameters extremely slowly is not going to be the asymptotic limit that's relevant in delta F, where delta W is less than F. Because that asymptotic limit is an asymptotic limit for evolution while in thermal contact with the heat bath. Well, the process you have there is you want the relevant quasi-static process says take the system, operate on it extremely slowly relative to the equilibration time with the heat bath. And of course, that the process you get out if you run this process asymptotically slowly is going to asymptotically move you to a different equilibrium state at a different temperature. So I don't think this is a huge issue, but I think for your purposes, there's no reason you shouldn't be, other than the fact it's slightly harder to derive, there's no reason you shouldn't be using the version of the Jasinski equality that holds while the system remains dynamically coupled to the heat bath. And I think you need to use that version for the purpose you're using it for.
Yes, okay, but is it the point that so it's for my? Is it the point? The point is not that this does not hold.
Oh no, sure it holds. I mean, as a special case of the fact that it holds under extremely wide assumptions about the coupling, it will certainly hold if you just decouple them entirely. Yeah.
Yes. So I use it like this. So okay, yes, I take the point.
Yeah.
I thought that this was a better way to do it, just because if you do it like this, then it becomes very clear that your final state does not have to be canonical for the temperature.
But that's true anyway.
That's
true anyway. And I think I haven't worked this through, but I think if you do it the way you've got, the asymptotics won't turn out quite right. So there's an answer to what happens if I adiabatically and quasi-statically transform the system. But in that situation, of course, the work I can get out will equal the change of energy in the system. It won't equal the change of free energy. It'll only equal the change of free energy if the system's coupled to the heat bath.
Yeah, I see. Okay, thank you.